Okay, so what we are doing here is we're making an inferential statistic, or a test statistic, that is going to be used to determine what is true. Are we going to reject an H0, are we going to, and therefore accept the alternative hypothesis, or are we not going to be able to reject the null hypothesis? Alright, now, the weird thing about, okay, descriptive statistics all have names like mean and variance, average and variance and correlation and stuff like that you've probably heard of before. The test statistics or inferential statistics either don't have names or have weird names. Like, for example, because we're trying to test for the difference between two means, we're going to be doing the difference between two means statistic, which doesn't exactly roll off the tongue. It's Z. And Z is going to be then a measure of how different two averages are. And I give you the equation there for it, but let me be clear. We are not going to be looking at that, doing anything with that equation. I don't want you to memorize that equation. I don't want you to be able to solve problems with it or whatever, but we're going to be using this as a way to understand how errors can happen in your experiment and so on shortly. So we're going to need to be familiar with what the equation looks like, but we're not going to be memorizing it or anything like that. Z is a measure of how different two averages are, like the average height of a Creighton student and the average height of a UNO student. This is going to be a measure of how different they are, and if they're too different, we can't keep our null hypothesis that the means are actually the same. Z is brilliant. This Z statistic was derived in such a way that has great properties, and one of those great properties is that if the null hypothesis is true, Z will have certain properties, namely it'll be distributed according to the standard normal or bell curve, which, you know, looks like that, okay? And so if H0 is true, we would expect Z to be mostly under the hump of this distribution and every now and then way out in the tails. If we get some weird value of Z, like it's way far out in the tails of the distribution, apparently that wasn't very likely to happen under the assumption that H0 was true. So if we come up with some weird value of Z, where Z is the difference between these two averages, apparently the null hypothesis isn't true. We came up with too big of a value of Z for H0 to be true. Alright, so since this is the distribution that Z is going to have if H0 is true, if we come up with something that isn't consistent with this distribution, apparently H0 isn't true. And we'll get to reject H0 and we'll get to accept the alternative hypothesis. But now, in order to get there, let me work with a bigger version of that diagram, because I think that this is a little bit, working that tiny little corner isn't such a great idea. So what we're going to do is we're going to say, hey, if H0 is true, Z will be distributed according to this little histogram of this bell curve here. And that means that it's like most likely the value of Z would be near 0, and it's less likely that it's going to be out here in these little, way out here in the tails of these distribution, because the curve is lower there. So if we compute Z and the value we get is way out there in the tail of the standard normal bell curve distribution, it's unlikely that happened. Under the assumption that the null hypothesis is true, we get to reject the null hypothesis. And if you reject the null hypothesis, we got nothing we can do except accept the alternative hypothesis, because they are exhaustive and mutually exclusive. This is not the same thing as proving that that there is a difference between the two means, or that there isn't a difference between the two means, but this is evidence, okay? We can then use this to build confidence in our results and so on. But it is not the same thing as proving, like in a high school geometry class when you proved that the sum of the angles in a triangle were 180 degrees or something like that. This is not proof, okay? The word proof in science is a difficult thing to work with here. But it is extremely unlikely that, I mean, the reason why it's not proof is because these things could happen just by chance. We could have ended up with an unlikely value of Z way out there in the tail of the distribution. It's not very likely to have happened just by chance, but it could have. I mean, no matter where on this curve we want to have a value of Z to be. Let's say we came up with a value of Z of like 2.4. That's pretty far out there in the tail of the distribution. On the other hand, if I look at that area I colored there in red, that area is proportional to the chances that could happen. I mean, there is some finite probability that we would get even bigger values of Z just by chance. There is some finite chance that I had bad luck when I made my choice of the Creighton students and the UNO students. And I just happened to get 10 really tall Creighton students, or I just happened to get 10 really short UNO students. That's an error. I really want the samples to be representative of Creighton and representative of UNO, but it happens. you get bad data, you get some observations that are wrong, there's a finite probability that the value of z, which is a measure of the difference between these two averages, is going to be big just because I made a mistake when I conducted my experiment and I drew 10 tall Creighton students. Rats. For what it's worth, by the way, that value is called p. I know a lot of people who take this class are like, social science majors and things like that, and they often talk in terms of like p statistics and so on. The p is the probability that this result could have happened just by chance because of like a badly conducted experiment. And since I know like in psychology, sociology, anthropology, they often work in terms of p, I thought I'd tell you that. When you conduct an experiment, p is the probability that you got these results just by chance, by a bad experiment. Alright, so if z is like an example of an inferential statistic or a test statistic, I mean, it's not something simple like average or variance or correlation, it's just a measure of how different two averages are. It helps us make a decision about the underlying process. Are Creighton students taller or shorter than UNO students? It's helping us make inferences about the world rather than just describing the world, like the average height I got was this much, or the correlation between these two groups was such and such. It's not describing it, it's helping us understand the underlying processes. So we're going to compute this value of z that is a measure of the difference between two averages. In fact, you can even see it there in the numerator of the definition of z. And then there'll be like tables in mathematical textbooks or stats textbooks or science textbooks that help us know what the value of z, how unlikely, how far out in the tail of the distribution is it going to be. Because if z is just too unlikely to have happened by chance under the assumption that the null hypothesis is true, then we're going to have to reject the null hypothesis and accept the alternative hypothesis. We're going to see how you do that and what errors can happen and see some examples and so on shortly. But before I do, and before we move on to that third part of the lecture, let's actually move on and talk about question 3 real quick. Question 3. In our examples, if this test statistic z was sufficiently large, we were able to A, accept the null hypothesis, B, reject the null hypothesis, or C, reject the alternative hypothesis. Which of these is what we do if the value of z is big? Alright, look at those 3 options, make a choice, and get a little feedback before you move on to question 4.